This PowerPoint is over electrostatics. Now the term electrostatics actually, electro is a word that means charge and statics is mean sitting still. So basically this is about charges that are sitting still. First of all, we're going to discuss the parts of the atom. We got three parts of the atom, major parts. You got two on the nucleus, two parts in the nucleus, and one on the outside in the cloud. And this object here is going to be a proton. This object here is going to be a neutron. That makes up the nucleus, and then we got the electrons that are going around the outside of the nucleus. Now the charges, proton is going to be positively charged, neutron is neutrally charged, and electron is negatively charged. And it's important to realize this before we start moving forward. Protons and neutrons that are in the nucleus, they're in the center of the atom. They're extremely hard to move, and for what we can do in a physics class, we can't really do anything. So it's essentially impossible to remove or add protons or neutrons to an atom. However, electrons can be removed or added fairly easily. As a matter of fact, just rubbing your hands together, you can exchange electrons from one thing to another. So in order to change the charge of an atom, we have to either add or take away electrons. That's the only way to do it. So we can't add or remove protons. We have to add or remove electrons. So to make something negatively charged, we're going to add on electrons. To make it positively charged, we're going to remove electrons. So in our electrostatics lab, basically what we have is we have some setup, and I'll use the example of the paper pickup. We have some pieces of paper that are sitting on a plate, and we got a comb and a piece of flannel that we can use to charge the comb. Initially everything's neutrally charged, that we haven't done anything to transfer charge from one thing to another. We rub the flannel onto the comb, and what that does is that charges the comb, that either adds or removes electrons. We really don't know which one, but we do know that there is a charge that's transferred. So let's just say that the comb is positively charged. Well, if it were positively charged, that means we had to remove the electrons to make it positive, and that makes the flannel negative. Now this positively charged object comes close to the paper, and the paper is neutrally charged, but what makes it neutral is that it has the same number of positives as it does negatives. It's not neutral because there are no charges on it whatsoever. It's neutral because we have just as many of the positives and negatives. Now the positively charged comb, when it comes close to the paper, it actually picks the paper up even though it's neutrally charged. The reason for that is the electrons, the negatively charged objects in the paper, are attracted to the positive comb, while the negatives are pushed away, they're repelled from the comb. Something we're going to be learning a little bit later is that with electrostatics, the electrostatic force depends on distance. So the further two objects are, kind of like gravity, the further two objects are away, the force of gravity, or the electrostatic force, is going to be less. And this is referred to as the inverse square law. So the closer they are together, the stronger the force is going to be. So if we think about those two charges that are in the paper, we got one positive that's repelled further away, that's pushed further, so it has a bigger distance, and then we have the electrons that are pulled closer, so it has a shorter distance. And because it has a shorter distance, the electrons are going to have a larger force, and they're going to be attracting. And then the repulsion of the positives are going to have a lesser force because they are further away. So the attraction is going to be a larger force, and it's going to end up attracting. And really, if we went back and we started with, well, what if the comb had a negative charge? Well, if the comb had a negative charge, then it would push the negatives away and pull the positives closer, and hence the positive and negative would still have a greater attraction than the repulsion of the two negatives. And that's kind of why we don't know what charge the comb is, because either way we get the same results. So it's kind of hard to pick which one when we get the same results. All right, this diagram just kind of shows the two different forces that are between charges. We got the positive and the negative that always attract, and the negative and negative that always repel. And this diagram actually shows that glass will always be positively charged and rubber will always be negatively charged, at least in most circumstances. That's how the charge is usually going to be distributed. Rubber is going to be picking up electrons, while glass has the electrons removed. All right, so there are three ways to talk about charging objects. The first way is actually what we did in our lab, and that's through friction, where by rubbing two objects together, you actually get some electrons that come off. The second method here is you have this charged object that's already here, but what it's going to do is it's going to have the positives come closer and the negatives that are further away. And if you actually touch these two, this is going to be charging by contact, and some of those electrons are put onto this sphere that has a charge, and the negatives actually transfer on there, which leaves a negative charge on the sphere after everything's said and done. That the negatives want to push away from each other, so they push onto the sphere, so that the sphere has a negative charge. The third method is to charge by induction, and basically what that is we start with an object that's electrically neutral. We have just as many positives as we have negatives. Then we bring a negatively charged rod close to it, and what that does is that pushes the negatives far away and pulls the positives closer, and then we actually touch the end of it. What that does is that grounds the rod. It allows the electrons to leave because they want to push as far away from these negatives as possible. Then when we remove the ground, basically what happens is we're left with a positive over here because the electrons had already left. So what this is transferring charge without actually touching these two. Then the electrostatic force pushes the electrons off of it, and then that leaves behind a positive charge, and that's the induction. This is a Van de Graaff generator, and basically what this does is this rubber band that goes around has a positive charge because the electrons are being pulled off down here by the brush, and then it goes up to the top here, and then it pulls the electrons off this metal dome, and then those electrons come back down and lets those electrons go. So basically it transfers the the negative charges off the dome here and transfers it to the ground here. And what that does is that leaves a large positive charge on the dome that which when something comes close that is negatively charged or even neutrally charged, that charge will actually transfer over and it'll make essentially a big lightning bolt. And this is a demonstration that we do in class. Next thing we're going to talk about dipole. The term dipole, what it means is that basically, we can think of the paper that we had the demonstration before in the paper pickup. When the positive cone came close to it, the positives were pushed away while the negatives were pulled closer. Now the paper is still technically neutral, but the charges are shifted away from each other to where there's a positive end and a negative end. Well, water is actually naturally dipole. And this is a very important thing, especially for life on Earth, because what happens is water actually splits up the positives and negatives that are in things like salt, sodium, and chlorine, and then allows the electrons to move freely. And those electrons moving is what gives us our electrical impulses in our body to be able to function and move and think and do things like that. The reason water has a natural dipole is because it has two positives here that have the hydrogen and the oxygen right here that holds on to the electrons. Now there's a covalent bond between the oxygen and the hydrogens, and basically what covalent means, it means it shares the electrons. But the electrons don't equally go to both of these atoms. What they do is actually the negative charges that stay around the oxygen atom more often, and that's actually what this symbol means. It's a delta. It's a lowercase delta negative, meaning that the charge is mostly negative for the oxygen atom and then mostly positive for the hydrogen atom. And as that electron transfers back and forth, mostly staying around the negative, or I'm sorry, around the oxygen, you can kind of think of this as two parents that are divorced that are sharing a child. The mom may get the child 5 days a week on the weekdays, and then the dad gets the child on the weekends. But the mom has more custody of the child. That's the same thing here. The oxygen atom has the electron more often than the outside. So the outside hydrogen. So the positive charge over here and the negative charge over here creates a dipole. Electrically, it's all neutral. There's just as many positives and negatives inside of this molecule, but it's shifted to where one side is positive and the other is negative. And basically what this does is this dipole nature, there's a demonstration I do in class where I have a charged rod that I put close to water, and the water will actually shift around to where that rod is negatively charged. The positive end will actually attract toward it and actually bend water. It's a pretty cool demonstration. So the electrostatic force is actually a field force, and what that means it's a force that acts over a distance as opposed to two objects that are touching each other. You don't have to have the charges touching each other in order for a force to be applied. That's the same as the law of gravity, and we're going to look at the law of gravity. If you remember from before, it's the force of gravity is going to be equal to the gravitational constant, which is 6.67 times 10 to the negative 11 times mass 1 times mass 2 divided by the distance between the two squared. And the reason I bring this up is because Coulomb's law looks very, very similar. We have the electrostatic force times Coulomb's constant here, which is 9 times 10 to the 9th newtons meters squared per Coulomb squared. Don't worry too much about the units here, just the 9 times 10 to the 9th. As long as everything in here is in base units, then there's not much to worry about with those units. And then we got two charges on top, charge 1 and charge 2. These two charges, the amount of charge affects how much electrostatic force there is between the two charges, and the more electrostatic force, the more charge, the more electrostatic force it's going to have. And it's measured in coulombs, and that's going to be a new unit for us for charge, a coulomb. And then we have the distance between the two objects, which is measured in meters. The force is going to be along the line of the two charges. So we got two charges that are either going to be attracting toward each other, or they're going to be repelling away from each other. So we don't have any forces here that are going to be perpendicular. There's no force coming up here or down, which may seem kind of ridiculous, but there are some forces. The magnetic force, the electromagnetic force, actually can be perpendicular with the charges, but we're not going to get into that right now. Basically, the force is in line with the two charges itself. Positive and negative will always be attractive, and repulsive forces for the positive, positive, and negative, negative. Now, if you think about the electrostatic force equation, the electrostatic force equation is charge 1 times charge 2. If we take this positive and multiply by a negative, we're going to get a negative force. And what that negative means attractive, because we know a positive and negative will always attract each other. If we think of two positive charges, positive times a positive will give us a positive force, which means repulsive. The negative times a negative will also give us a positive, which means it's going to be a repulsive force. So the electrostatic force equation will actually tell us whether it's going to be attractive or repulsive. Now, sometimes we don't really need to worry about that because we know positives are going to repel each other. We know a positive and negative is going to attract each other, so the negative we can kind of ignore. But the electrostatic force does actually tell us the direction of the force. Now, this direction is different than what we've dealt with before. The direction is either in, which is negative, or out, which is positive. And then we have to translate that over into the directions we're used to, which is going to be left and right. And we'll do that in some of the examples that we do in this PowerPoint. The inverse square law, this is true with gravitational force. It's also true with the electrostatic force. Basically what it means is the force decreases by the square of the distance. So if I have these two objects that have a force between them, if I double the distance, then what that's going to do is that's going to have 1/4 the force. Now think about that. Twice the distance, 2 times the distance, the inverse of that is going to be 1/2, and then 1/2 squared is going to be 1/4. So with twice the distance between the two objects, we're going to have 1/4 the force. That's the inverse square law.